All right, welcome everybody to week 16, day 1. Do we have class on Wednesday? I don't even know. I think we do, right? So, if we don't, let me know on chat, because students usually know what days you have off better than professors. We'll just be here and talk anyway. So, Thursday, no class, yeah, but we're going to be here on Wednesday. Okay, cool. Have I created my own wallpaper? I mean, technically, but it didn't look very good, so. So today we're going to be talking more about linked lists. This is a topic that's really a CSI 41 topic, but we'll go through just like a little bit of it so that it'll be easier when you get to 41, because it's usually the hardest topic in 41 for students to get. It's up to me if I want to have class or not on Wednesday. Really? We just say no class? That'd be cool. So we're going to be doing histogramming, right, for the Bridges Shakespeare assignment. And after we do the histogramming, that's what we talked about on Friday. After we do the histogramming, we're going to build a linked list. And so, really? I didn't know that. Tempting. I'm going to show you guys the basics of a linked list. So a linked list looks like this. Struct list. And let's say that we're making a list of words or whatever. String stir. And here is what makes it a linked list. We're going to make a list pointer called next. Okay. So this is a data structure that holds a single. It holds a single string, and it has a pointer to optionally another list. It's a recursive data structure, and I guess we'll talk about recursion today because that's been kind of exploding your brains a little bit as well. So let's initialize next to be something called null pointer. Null pointer means that it's not pointing at anything. So pointer can either point at something or it can be pointing at nothing. And this means the pointer is pointing at none. Okay. Pointer is pointing at nothing. Technically it's 0. Memory address 0 is the null pointer. Okay. If you've ever played Borderlands 3, there's a rifle in it called the Null Pointer. This one. So, Null Pointer. Okay. That's that. It's a very common. Use this for your Pokemon search function if it didn't find. Yeah. So, oftentimes, why am I out of focus here? Oftentimes, null pointer will indicate something was not found. Right? Because if you search a list to try and find something, it'll either return a pointer to the list where it does find something, or this thing is just not focusing. Or it'll return null pointer if it's not found. Yeah. Either way, you don't need to see my face. Okay, so what can we do with this? How can we use this? Well, let's just start off by just building it by hand. Now, normally we don't build these things by hand. We have functions to add to the beginning of a list, add to the end of a list, search a list, things like that. We're just going to do it by hand right now. So let's say that we're going to be we want to use the list to store a list of, what do they use in Zybooks? Like a grocery, like a shopping list or something like that? Is that what they use? You guys remember? Let's say that we're going to use this to track what we need to, evil shopping list. Okay, sure. So we'll have a item, which will be the item we want to buy, and we'll have a int quantity, which is how many of it we are going to buy. Okay. So this will be called a shopping. That's a shopping list. Okay. So let's go ahead and make one. So we can say list pointer A. I don't know. I got no better names than this. Is equal to new list, and it's going to hold I don't know, bananas, banana. We're going to buy 6 bananas. Okay. And its next pointer is going to be null pointer. I technically don't need to type this because if I don't type it, it'll initialize like this. Because I gave an initializer in here. But I'll just do that for the sake of completeness, or not really completeness, but just so you can, too many undos. There we go. Banana. Space it out a little bit. Okay. So this is going to create a new list. Now, every time you have a new, you need a what? Wallpaper Engine is the best $4 to spend on your computer. Yeah. It's pretty. It's really pretty. Every new needs a delete. Very good, Mr. Bringus. Why does my face keep getting covered up like that? Strange. Always on top is on. Odd. There we go. Strange. Okay, then main.cc. So yeah, so this is going to make that, and then like Mr. Bringus said, we need a delete, so we need to delete. Every time you do a new, you need to delete. And if this looks annoying to you, it's annoying to me too. This is why we don't do it this way usually. Okay, so I'm just kind of doing this by hand, right? Doing this by hand. So let's add another item to our list. Let's call this one B. And this one will be buying peaches, and we will get 2 peaches. And now we want, what do you have? What do you want to have first in the list? Do you want to have A come first or B come first in the list? Wanted Air Jordans, not fruit. Next one could be Air Jordans. How about that? C. Air Jordans. Who the hell keeps texting me? Yeah, just want to make people at work. It's fine. Okay, so the problems of being popular. Well, you know, it's a coworker. You have to. I guess you technically don't have to check, but he's just talking about the new Alder Lake, PCI Express, DDR, you know, all the new revisions coming out right now. Okay, which one do you want to have first? Do you want these to be alphabetized? Like, just tell me which one you want to have first in the list, because the list is going to be ordered. So list is ordered. That means there's somebody who's first, there's somebody who's second, there's somebody who's third. That's different from an unordered map where there is no ordering. You know, you just say bananas 6, Air Jordans 1, right? And you don't say, well, bananas are first in the list. There's no ordering with an unordered map. It's right there in the name. So A, you want A to be first? Do you need to delete B and a delete C? Yeah, you do. Yeah, you do. And this is why it's annoying. And this is why I don't write code this way. Oops. There we go. Thank you. So you want to just have A, B first, then B, then C? Or you want to alphabetize it? Air Jordans come before bananas? What do you guys feel like? Reverse order. You want reverse alphabetical. Okay. Sure, that's evil order. All right, so, okay. So B points to next equals A, B, then P, then A. Okay. A points to next is equal to C. Okay. So B is first in the list, then A is second, followed by C as third. You're hurting my brain here a little bit, but that's fair. That's fair. Linked list should hurt your brain a little bit too. So, all right. So now let's write a function to print out all the elements in the linked list. All right. So it's like golf. For list pointer temp equals who's the head? B. B. As long as temp is not equal to null. I'll do it the long way, but you can actually just say this. Null is 0, right? And so 0 is always false. So you can actually just say that if you want to be, and everybody understands that. But I'll do it the long way for now. It's your first time seeing it. So we're going to start at the head of the list, the beginning of the list, which is B. And we're going to end once we hit null pointer, and we're going to say temp is equal to temp points to next. This pattern here, this is the clutch pattern for iterating across a linked list. You're gonna write this for loop a lot of times, and in C/41, maybe not this many times. You just bought Wallpaper Engine. Nice, very cool, very cool. So, so what this is saying is starting at the front of the list until you run off the edge of the list, go to the next one, and all we're going to do is print out the name and the quantity. And there you go. Peaches 2, Banana 6, Air Jordans 1. Okay. So that is creating a linked list, iterating across a linked list, and deleting a linked list. What was the shorter bool condition? Just temp. Yeah, because null pointer is 0. 0 is false. So, and null pointer is 0 for this reason specifically, so you can do that. So let me draw out what's going on here for you, and maybe the graphics will help a little bit. I don't think this is too hard to understand, but Jensen's reverse alphabetical ordering might be hurting people's brains a little bit. I don't know. Let's find out. Let's switch over into OneNote. So, 40. All right. So, what we've done is we've newed 3 chunks of memory, right? That's what new does, right? It allocates a block of memory, and that block of memory sticks around until we delete it. Okay, so how much memory does it allocate? It allocates enough memory to hold a string, an int, and a list pointer. So when we say this new here, after this line of code, that's a horrible block, isn't it? After that, I can do a shape, can't I? Look at you. Aha. All right, neat. Don't have to freehand stuff now. So this is, we're going to call A, I guess, because we have no better names for stuff. So A is a pointer, and it's going to point at the very beginning of this chunk of memory here. And there's 3 parts to this chunk of memory. There is the string item, there is the int quantity, which I'm not going to spell out, quant, and there is another linked list pointer, or list pointer technically, named next. Okay, so when we call new, it allocates this memory somewhere on the heap. This is somewhere on the heap somewhere. It's the heap's like all over the place here. Somewhere within the heap, there's going to be enough memory allocated to hold all that stuff. Okay. Yeah, the arrow operator is the dot operator when you have a pointer. It's the exact same thing as the dot operator. It just dots don't work with pointers for whatever reason. It's something I kind of wish it had changed. Honestly. In Java, it's dot for everything, for example. Okay. So, and when we start this off, next is going to be pointing at null. Okay. This would be set to banana, and this one would be set equal to 2. Okay. So we allocate a block of memory. We set item equal to banana. We set peaches, or we set quantity equal to 2, and we set its next pointer to null. That's after we run this line of code right here. Banana. Yep, I knew Margaret would get that reference. Okay, so missed you at meditation yesterday, Margaret. It was a good time. It was cold again. It was nice at the beginning. It was 66 degrees. It was pleasant. And then by the end there, it was just like, meditate on having a fire in front of you. Imagine you're at a bonfire. Yeah, okay. So that's after this line of code here. Second line of code then runs and somewhere else on the heap. It doesn't have to be right next to it. I'm just gonna scroll kind of randomly around here. You know, I should use the square tool again. That was really nice. Okay. And then somewhere over here, we're gonna allocate another chunk of memory. They don't have to be next to each other. They might be. They're probably not. Or they could be. Who knows? You don't know. I don't know either. It'll just be somewhere. And so this one's going to be called B, and B is going to be pointing at the very first byte of memory here. And this one's item is going to be peaches. Millions of peaches, peaches for me. Millions of peaches, peaches for free. Quantity is equal to 2. And its next pointer is going to be set equal to null. Also. Or I can draw that pointing to 0, either way. Same thing. Yeah, no worries. And then we run the next one, and that one I'm going to just scroll over here kind of randomly again. And I'm going to allocate a block of memory for C. And this memory gets allocated. It's permanently allocated until we delete it, right? So, all right, cool. All right, cute. Not selected. Thank you. All right, so this one is going to hold Air Jordans, and it's got a quantity of 1, and its next pointer is also going to be pointing at null. Okay. So this is the state of affairs. This is what's going on inside of RAM. What we're looking at here is RAM, and I'll just make this consistent. Its next pointer is also pointing at null. So technically they're all pointing at the same place, but I just don't want to draw them all pointing at the same place. I guess I could. Either. They're all pointing at null. So now we're going to link them up, and that's why it's called a linked list. Because we got a list and they're linked together. So instead of just having all these guys kind of hanging out separately, what we're going to do is we're going to put them in an order. And again, this is usually done inside of a function, but I'm just kind of doing it manually. Yeah, you were missed, Esterberg. You were missed. So B points to next equals A. So B points to next is this fellow right here. And so rather than pointing at null, B points to next equals A. A is pointing at that spot right there. So what it's going to copy is the memory address held in A. Remember, pointers are just memory addresses. So they're 64-bit numbers that just hold a spot in memory. Okay. So so B, rather than pointing at null now, is going to be pointing at the same location that A does, which is that spot right there. Okay, the beginning of item, basically. Then we say A points to next equals C. So A's next, rather than pointing at null, is now going to be pointing at C, which I didn't draw on the screen, did I? So C is pointing right here. Okay. and so it just copies that memory address over. Remember, all a pointer is just an int. That's it. Nothing fancy. There's nothing crazy. It's like an art class, yeah. I mean, you know, I don't know if the art instructors can freehand a circle as well as I can, but I mean, you know, add some shading to it. There you go. My NFTs are going on sale any week now. Thank you for screenshotting that, Jensen. I appreciate it. Real. Yeah. Can I freehand a circle? No, not really. Okay. So we are now going to do the for loop. So do you guys have any questions about this? So we've got, I'm just sort of drawing out RAM. You know, like these are just different parts in RAM. And all of RAM addresses is just a number. Okay, so when you allocate a block of memory, there's just a number that the block of memory starts at, and that's just what's returned. All new returns is an int, and the int is just the spot in RAM where the thing lives. And so when you say b points to next equals a, it's just copying that integer into b points to next. So this guy's, the number in here, the memory address, the block in RAM is the same one that a is pointing to. That's all that's happening. There's nothing deep or complicated about it. The system was invented in the 1970s when you had to examine every bit of RAM and every CPU cycle intensively. So the values aren't pointing at anything until you say they are. They will be pointing at null, right? So these, so you see up here how I have an initializer on it, and in addition to initializing it here, I also initialize it here. So I could have deleted the null pointer off of all those. I just wanted to be like extra clear that by default a points to next is 0. Null pointer is just 0. In fact, I could I could write it 0 there. It compiles just fine. I could also write null like that. That would also compile just fine. Null pointer is the correct way of doing it, though. The trouble with this is that, you know, when you're looking at it, you're like, is that a quantity? Is that null? I don't know. You know, perhaps I'm buying 0 peaches, you know what I mean? Or 0 bananas. Like, when you see a 0, that really doesn't tell you, like, you know, anything about it. It's an int, right? 0 is an int. And so null is just an alias for 0. And so it gives you more of an idea as a programmer what's going on. That's supposed to be a null pointer. Technically, though, it's just an int. And if you do something wrong, like, you know, multiply by 2, type long. Yeah, that's fair. But you can multiply null by 2 because it's just an int. It's just 0. So, null pointer, however, you cannot multiply by 2. Null pointer, you can't do anything with it. It will get mad at you. You cannot multiply null pointer with an int. All right, null is just 0. So you can multiply it, you can add to it, you know, and a whole bunch of horrible things you should not do, but under any circumstance. So it's recommended to use null pointer always when you're initializing something to null. Okay, you'll see these though in like older code bases. Yeah. 0 irks me. Null is okay, I guess, as long as you're not multiplying it or adding to it or something. Null pointer will prevent those. It uses the type system to prevent mistakes. Okay. So, do you guys see how this is set up? So this is kind of like the head of the list. That's kind of the tail of the list. So it's B's first, followed by A, followed by C, because Jensen is a horrible person and wanted to do reverse alphabetical. Evil Jensen. Yeah. Okay. So let's do the for loop. I see Carlos is typing, so let me know if you have any questions. No? Okay. So let's do the for loop. So let's talk about what's happening here. All right. So we're going to create a pointer called temp. So temp is a pointer. Pointers are just integers. Under the hood, they're just integers. The type system doesn't let you easily convert to and from an integer to a pointer. Like, it tries to like hide the fact it's just an integer, but it's just an integer. And so temp is going to be initialized to be b. So when temp starts, it's the memory address in temp is the memory address of b. That's it. B's an integer, copies the integer over into temp. That's it. So we then look at the conditional in the middle of the if statement. Is temp true? So it's going to be some memory address like 5,972,000. That's true, right? Because 0 is false, everything else is true, right? So we then execute the code here. We see out temp points to item, so it's going to print out peaches, followed by a colon, followed by temp points to quantity, which is 2. So it's going to print out peaches, colon, 2. And then it moves on to the third part of the for loop, which is temp is equal to temp points to next. So temp is equal to temp points to next. Temp points to next is currently a, right? Why did you have to use new? Because they're pointers. Pointers work with new. They work with memory addresses, these things. If you made a regular list, yeah, it wouldn't be a linked list. I don't even think it would work. Okay, so yeah, temp equals temp points to next. Okay, so temp equals temp points to next. Temp points to next is a, so temp is now going to be pointing up here at a. We check to see, is temp null? Nope, temp is not null. Temp is pointing at a. We then see out temp points to item. We print out banana. We print out a colon. We print out temp points to quantity, which is 6. I don't know why I have a 2 there. That should be a 6. Okay. And cool. So prints out banana, colon, 6. Then temp equals temp points to next. So temp equals temp points to next. Temp points to next is currently pointing at C. So temp equals temp points to next. So temp is equal to C. Is temp null? Nope, it's pointing at C. That's fine. So we output temp points item, which is Air Jordans, colon, quantity of 1, and then we move on to temp points to temp equals temp points to next. Temp points to next is the number 0, so temp is now 0. Okay. Is temp true or false when temp is 0? It's false. So the for loop ends. We're done. We then deallocate A. We deallocate B. We deallocate C. And we're done. Yep. Voila. What great notes for today. Yeah, maybe I should erase this. Okay, I'll leave that up so you can look at it. Okay. Now, if I didn't delete one of those things, what would happen? Like, what bug would I have if I didn't delete A or something? Fine, right? Works same. -f sanitize equals memory address sanitizer. Checks for memory leaks, things like that. There we go. Leak sanitizer detected a memory leak. You allocated memory on line 14. 14 shift G. You allocated memory on line 14. You did not deallocate it. You were a bad person. So, yep. You guys see that? So AddressSanitizer is your friend. It's not your friend if you need speed, but it is your friend as a new programmer, as it will find out if you ever screw up. If you double delete. Explosion. Heap use after free. Line 26. It was freed here on line 26. You use it again on line 27. You're deleting it again. It was allocated on line 14. So it tells you everything that you need to know. So line 26, Shift G. It was deleted there. Deleted again on line 27. So, okay. Or if you delete A and then you use it afterwards, let's see out A points to item, points to quantity. Ethel the Shrew goes quantity surveying. So if I try using this list after I delete it, then it will explode also with a use after free error. You're using it after you've deleted it. That's bad. That's a no-no. Can't do that. Line 26, you allocate on line 14, you're using it on line 26. Okay. Now if I were to turn off AddressSanitizer, who knows what will happen? It's undefined behavior. Segball. There you go. 6. So A is bananas. Do you guys see this? So A points to quantity. It was 6, right? So I printed it out. It still had the number 6 there and RAM. You guys understand how terrifying this is, by the way? This is a use after free error. And it worked. You know how scary that is? No explosion, no crash, no seg fault. I deleted something and then I printed out, hey, what's in RAM at this memory address? Because a pointer is just a memory address. And so I went to that memory address and I went to its quantity field and printed out the value there in RAM, and it was 6 still. Why? Because we just hadn't done anything else with that spot in RAM yet. Why did it work? Because nobody changed what was in RAM. When you delete something, it doesn't zero it out. That would be very slow and inefficient. It does not zero out memory when you delete it. It's still there. It's just, it's marked as unused. So the next time you do a new, it might overwrite that spot. But maybe for the next 5 minutes, that spot will still be 6. And you're going to be going along and having a good time, printing out 6 over and over again. Then all of a sudden, it's 422,977,000. You're like, what the hell just happened? I never changed A points of quantity ever. You know, no, I never changed it, you know, and all of a sudden it just changes. You're just like, what the hell is going on? So you have to be very, 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 delete just marks that memory is unused. That's all it does. It doesn't actually erase anything. Okay. Is that why you can access a file you've deleted? Yeah, file deletions work the same way. They're just marked as deleted. So you can recover a deleted file sometimes. Depends if, you know, if you write another file, that spot's open, okay, it'll overwrite it, you know, but there's a good chance that they can pull the data off. Okay. So look, 6. It'll be 6 until it won't be. At some point, it won't be 6 anymore because that memory is unused. At some point, it's going to be reused, and then that number will change, and you will be baffled, absolutely baffled, that the number changed without you changing it. Yeah, it's why people defrag their drive. Partly, yeah. If you want to securely delete something, you have to overwrite it multiple times, and then you have to drill out the hard drive, drop it in an acid bath, scatter the fragments from the top of Mount Everest. then you'd be pretty sure it's deleted. But people can do a pretty good job recovering data off a disk a lot of times. So if you follow the DoD guidelines on data deletion, securely deleting things, it's actually fairly involved. Seen Elliot and Mr. Robot drill hard drives. Yeah. Mr. Robot is actually one of the few shows that they more often than not get the computer science correct. It's surprising to me. Like, and I'm not saying they get it right all the time. They proclaim a Raspberry Pi to be a hacking device, which it's not. But they do install a Raspberry Pi like in a data center. They like pop open like a thermostat and like install one of these things into it and use it to tap into their networks, their intranet, which is plausible, I guess. But they made it sound like a Raspberry. I know what a Raspberry Pi is. It's like it's some sort of like Uber hacking gear or something. Yeah. So I do give props to Mr. Robot for actually making an effort to try to have good computer science, because most Hollywood, it's just it's so bad it's embarrassing. It's so bad. Like, could you at least get the guy that does your website to like come in and just like look it over? Just like bring that guy in. He's probably the guy with a Slayer T-shirt, and a beard. And, just have him come in, just like look over your script. Like just pay him an hour's worth of his time, have him look over the script if you're going to have any hacking whatsoever. So yeah. So this is linked lists. If you're going to do this in a function form, you can do something like this. You can do void print list. And usually when you do linked lists, you're not going to do them by hand like this. This is sort of embarrassing. For your homework assignment, you're going to have to write 2 lines of linked list code, and you're going to set basically somebody's next using not this exactly. It's called the set next function. You're basically going to do b points to set next. Oops. Points to set next. Okay. You're going to do something. What's going on with these typos today? You're going to do something like that. So you're going to set the next of one of them to the other one, and it's your goal to determine that. Yeah, the comments in the Bridges Shakespeare code pretty much tell you what you have to type. You're basically going to have to do something like that, and then you're going to have to do one other like pointer copy thing. And I don't want to give away the comments. Kind of give it away, but I want you to figure it out. And the nice thing about Bridges is that if you screw up and you don't link up the things properly, when you visualize it, you'll see that those things are not linked up properly. Like, that's the beauty of Bridges, is that you can visualize a data structure and find out, I goofed up, I screwed up, because you can see it, One of the hardest things with programming linked lists and things like that is that unless you have a really good idea up here in your head, your conceptual vision of like what's going on over here, you're just shooting in the dark a lot of times, and that's why it's important to like draw things out like this, so you can actually kind of see what's happening and kind of understand what. Like Jensen had a moment on there when he went, oh, right? That moment of like actually understanding what's happening conceptually translates into you actually writing good code. If you don't, you're just gonna your code is guaranteed to just segfault and be terrible. Okay, so let's make a function here. We'll print list, and I'm going to turn this into a recursive function to tie in with our topic of recursion as well. So list pointer temp ly. It's so hard to come up with a good name. Okay, so list pointer ly. let's do that. So we're going to take a pointer named pointer, or putter, as Arthur Dwyer puts it, putter. Okay, so we're gonna just do this. So we're gonna who was at the head B. Okay, so we're gonna call print list passing in B, and that's gonna print the list starting at B. Same code. You guys see that? Same code. I just moved the for loop up to a function. So you can call print list B, but what's interesting is you can also call print list C. So what is it? What? How can you print C? Well, A is a list, and B is a list, and C is a list, right? So this is a recursive data structure. Every list has a pointer to another list. And so you can actually call print list on any part of the linked list, the beginning, the middle, or the end, and it'll work. And so if you call print list on the middle, then you get, was that in the middle or was that the end? C, oh, C is the end, sorry. Jensen. It's like that Who Wants to Be a Millionaire, where option A is C and option B is D and option C is A. And my answer is C, final answer. Okay, so, right, you guys see that? So if we pass in the middle part of the list, it prints the 2, and if we pass in the last element of the list, then it prints out the last one. Okay. So we have a function to do this. Now, blood alcohol counted. BAC. Okay. So let's see if is there a better way of doing this kind of stuff? Yeah, maybe. I don't know. Huh. Definitely. We could do shared pointers. But no, let's do recursion first. We'll not do the for loop, because remember, anytime you do recursion, it's basically the same thing as a for loop. So when I was up in Seattle for CPPCon, I talked to a guy who never learned for loops, at least in his first semester computer science class. He only learned recursion, because you don't need a for loop, you don't need a while loop. All they did for all of their loops was recursion. And they were in a programming language called Lisp. And Lisp is the list processing language. Everything in Lisp is a list. And so you could do everything recursively in Lisp. And so they would print a linked list like this. They would say, if pointer equals null pointer, so if you pass in a null pointer to me, with just return, we're not going to print anything. Otherwise, we are going to see out. They were forced to write recursive methods, baby seals. He's like, look, if you're introduced to recursion early on, it's just natural. For loops seemed unnatural to me because we just did everything in recursion, and so learning how to write a for loop just felt really weird. Okay, so if we pass in a list, if the list passed in as null, we return. This is what's called the base condition. And if it's not null, if there is something there, then we print out what's here. Like if you pass in B, it's going to print out peaches. Feels like it should be bananas because it's B. And so if you pass in B, it'll print out peaches and 2. And then rather than doing a for loop, what we do is we recursively call. We call print list, passing in pointer points to next. Call it a day. And we're done. Okay. So doing the same thing as a for loop here. It just looks different. Okay. So if you have to have the base condition in order to stop it from running forever, and then this is called the iterative step that moves it towards an ending point. The base condition and the iterative step are both required, and this is the meat of the functions. The meat of the functions we actually are doing, like we're printing, right? It's called print list. So we actually have to print something, but you need a base condition to stop it from looping forever, and you need an iterative step that always moves you towards the end. How would you do vectors in recursion? Same thing. You just, instead of a pointer, you just pass in an index. And so instead of print list pointer points to next, you would just print the vector with the index incremented by 1. And then you check to see, did I hit the end of the vector? If I did, bail out. If I didn't, print the current element, and then recursively call yourself on the next one. Can recursion always replace for and while loops? I mean, technically they're all interchangeable, but recursion only makes sense when the self-similarity principle is in play. So what is the self-similarity principle? That means the thing at a big scale looks like the same thing at a medium scale, which looks at the same thing as a small scale. So a single entry in a linked list is a linked list. A linked list with 1,000,000 elements in it is a linked list. Linked list with 2 elements in it is a linked list, right? Every node in a linked list is a linked list. And so every list, this is a recursive structure, right? Every list points to another list. It's a recursive structure. It exhibits the self-similarity principle. Therefore, when you mess with things like linked lists, it's very binary trees too, which we'll learn in 41. Anytime something is self-similar like this, every list has a list, then recursion is a good option. Technically, you can always convert back and forth between a loop and a for loop and a while loop and a recursive loop. That said, should you? No. Just because you could doesn't mean that you should, right? Jurassic Park. So, linked list is a lifestyle. Yeah, the Lisp language is built on lists. That is their pride and joy, and their defining data structure and stuff. Yeah, don't need an array when you got a list. You know. Okay. So let's say we wanted to build up a linked list by a function or something. What time is it? 12:54. First of all, any questions about recursion? I know some of you. While we're on the topic of recursion, before I go back to talk about lists, I know there were questions about recursion. So if you have any questions, ask them now in chat.
You want to say goodbye to them?
Are they leaving?
Yeah.
They're both leaving? Okay.
Only Mr. Ben.
Yeah. I'll be right back, guys. Post your questions in chat. All right. Welcome back. Sorry, we had a guest over. I wanted to say goodbye. What is the purpose of an iterator? An iterator is basically the same thing as a pointer. They're a class. Pointers are just integers. Like there's nothing crazy about a pointer. They're literally just integers. An iterator is like a class. Like, you know how you can make a class, like class iterator. And somewhere within an iterator there's going to be a pointer, but iterators do more fancy stuff. Like if you have a pointer to an element in an ordered map, when you say go to the next element in the ordered map, how does it know how to do that? You know, like there's actually some crazy logic that goes on behind the scenes to make that work. And so it's more than just like an integer, you know. So, but I will deliberately use the term pointer and iterator interchangeably, even though it's wrong, just because kind of conceptually they work the same way. Can you give a visual representation of recursion in a function like recursion was inside of a for loop? I wouldn't do that. I wouldn't do recursion inside of a for loop. I'd use one or the other, probably. All of lab 1 can you link other data structures or just lists? Yeah, the let me blow your mind now and introduce another topic from CSI 41. There you go. And this is something called a binary tree. So a binary tree has a left pointer and a right pointer. It's got 2 pointers instead of 1. Okay. So that one also exhibits the self-similarity principle. Every tree is also, its child is a tree, and its child's child is a tree. And so you can write recursive algorithms to loop across them. Yeah, BSTs, the binary swole tree. Right. Okay, so you wish you didn't see that. Yeah. So you want to look at lab 1 on Zybooks? Sure. Okay. Zybooks.com. Recursion. All permutations of names, that one? Okay. So, program lists always will line for a photo. All permutations of a list of strings. The program will read a list of one word name until a -1. And use a recursive method to create and output all possible orderings of those names, separated by a comma, 1 ordering per line. When the output is Julia, Lucas, and Mia, it will go blip, 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 blip. Okay. So, all right. Name list, perm list. Bring a list of names, stop when -1 is read, then call the recursive method. Yeah, so what I'd do is I'd start by picking one of the names and then basically looping across all the possible names and pulling it out of the vector. And then print it, pull it off the vector. I'd probably not use the vector, I'd probably use like a deck or something. But basically then recursively call myself with the other 2 names. And then they would pull the first one off and then the second one off and recursively call like that. So that's basically how I do it. I'd go through all 3 of the names, pulling it off, recursively calling on the remaining 2, pull one off, recursively calling the other one, and you'll see it goes Lucas, Mia, Julia, Julia, Lucas. It'll go through however many are remaining on it. Kind of a pain. I don't think I'd enjoy writing that. So yeah, no, it definitely is a puzzler. Yeah, definitely makes you think about it for a second. Yeah. Okay. Seems like a CSI 26 problem. What is a union? All right, asking the good questions today. All right, so union of bakers, right? No. Teamsters, no. Union Bob, int A, float F. I apologize for what I'm about to do. All right, so bob.a equals 42, cout bob.a. Bob.f is equal to 3.1415. Cout bob.f. Looks like a struct, right? Looks like a struct. Got a member variable and a f member variable. Okay. And in fact, when we print it out, we get 42 and we get 3.145. Cool. Everything makes sense. Everything makes sense right up until this moment. See how the size of Bob. How many bytes is Bob? 4. Bob is 4 bytes. It's not a mistake. What is the size of Bob's integer? What is the size of Bob's float? Well, those are both also 4 bytes. 4, 4, and 4. Yeah, so watch what happens. Right, we set Bob's integer to be 42. We set Bob's float to be 3.1415. Watch what happens if we print out Bob. Let's do this so you can remember where we are. So we set Bob.A to 42. We set Bob.F to 3.1415. Then we'll print out Bob.A again. Here's a question. Did Bob.A change anywhere between this printout and this printout? Did I use the words Bob.A equals anything in here? Guess what? There's only 4 bytes in Bob. Guess which memory gets reused? It's the same memory address. So Bob.A and Bob.F share the same spot in RAM. That's what a union is. A union is a way of avoiding wasting RAM. We don't use it very much these days because RAM's cheap, you know. But like, let's say that you only needed to, let's say that you have a database, and the database can hold either dogs or people, and people have social security numbers, and dogs have dog tag numbers or whatever, right? You could store the social security number as a union and have, let's say the dog tag is a different type than social security. You could store it as a union because you know if it's a dog, it'll be a float, and if it's a person, it'll be an int, or something like that. You don't have to store both of them. That's what a union is for. Yeah, sorry about that. We don't use those very much anymore. There's a C++ thing called Variant, which does that better. So variants sounds like something from the Marvel universe or something, Loki or something. So a variant means this can hold either an int or a float, and it's just a much nicer way of doing it. So we don't use unions anymore; we use variants. And so if you set v equal to 42, then it contains an int, and you can get the int value, and it returns 42. And if you try getting a float out of it, when it holds an int, it's not allowed. Like if you try using this as a float, when it holds an int, it knows that, and it won't allow it. It'll throw an exception. So it's a much safer way of handling these things. So this can either hold a string or a void pointer. Interesting. Yeah, and so you can find out which version of it is holding. It's just a nicer and better way of doing it. Union is garbage. Well, it's not garbage. It's just if you don't know what you're doing. All right. The Phantom Thieves. Yeah. So, I don't know if I want to introduce smart pointers. We've got 3 minutes left. Let me show you a better way of doing this, I guess. So, null pointer, then B is going to point to A, and C is going to point to B. How about that? Okay. Then we don't have to do any of this business like set next and stuff like that, which you do have to do for your bridges assignment. But you see what I did here? So when I made C, C's next is going to be B, B's next is going to be A points to null. And so if I print list C, then it prints Air Jordans, peaches, and bananas. It goes C, then B, then A. Okay, so you can just set it up that way. Usually though, you're going to turn this into a function where you typically will have something like this. You'll have like a list pointer head equals null pointer, and then do something like this while let's get rid of all this. Okay. Let me show you the more proper way of doing this. While true, what we're gonna just like read in groceries to buy. So we're gonna have a pointer to the head, we're gonna have a pointer to the tail. Okay, so string item equals read. Please enter thing to buy. Int quantity is equal to read. Please enter how many to buy. Okay, and then if this is the first thing that we're adding to our linked list, we need to set head and tail, right? So head is the beginning of the list, tail is the end of the list. So the first time we add something to the list, these things are set to null, so we need to point them at it. So if head, yeah. So let's do this. List pointer temp is equal to new list passing in item and quantity. So we're going to make a new node in the list, and then if we've never seen anybody before, if head is null, then head is equal to tail is equal to temp. So the new person we just allocated is going to be the head. The beginning of the list is pointing at it. Tail, the end of the list is pointing at it, and we're good to go. Otherwise, if the list exists, new list. Otherwise, the list exists already. Then, if the list exists already, then we don't mess with the head because we're always going to be adding to the tail of the list as we add entries and stuff. Then we will say tail points to next equals temp. So this attaches the new node to the end of the list. So whoever was last in the list, their next is the new person, and then the new person is now the end of the list. Like that. So we need a new chunk of memory. The old last guy, his next is pointing there, and now that's the end of the list, and we're good to go. That's it. That's all it takes to make a linked list. And then if you want to print it, we can just say print list head, and see what we get. Pairs are not the same thing as a variant. A pair is two things. So if you have a pair of an int and a string, it has an int and it has a string. The int's in first, the string's in second. A variant, if you write to the string, it overwrites the int. That's the same block of memory. So unions and variants use the same block of memory for both of their members. And so if you write to one, it overwrites the other. And so you can only have one or the other, but not both in it. It's done to save on memory costs. So please enter a thing to buy. I will buy peaches. I'll buy 10 of them. Grapes. And I'll buy one bunch of grapes. Air Jordans. Shoot. I can only read one word at a time. It's going to be air, isn't it? Raspberries. I'll get 17 of them. Oh, shoot. I don't have any way of ending this, do I? Alright. If quantity equals 0, break. Anytime you have an infinite loop, you should always have a break in there. Alright, so grapes, we'll get 10 bunches of grapes. Bananas, we'll get 21. Peaches, we'll get 16. Air Jordans, which has to be one word, we'll get one pair of Air Jordans. Reebok pumps, we get 2 of those. And there. Okay. And you can see it makes a list. Grapes, bananas, peaches, Air Jordans, Reebok pumps. And everything works. Okay. How are we getting out of the while loop? Yeah. Perches. Okay. So that is basically what your homework assignment is going to be about. First part, doing histogramming. We went over that on Friday. Look at that lecture to see how that's done. And the second part is going to be building up a linked list of all the different top words of Shakespeare. And you build up the linked list, and then there's bridges visualized that will render the linked list to the screen. And you can see if you did the linking properly. This part here is the part that's missing. Okay, this part here I did for you. But this part here where you set the new person, the old end points to the new person, and then the old end, the end now points to the new person. Okay. Those are the 2 lines you need to do. Except it's not points to next, it's going to be called set next. They actually have a function for it. And if you do that, you should be able to clear the homework assignment, no problem. It shouldn't be hard. It should not be a hard assignment. There's a little bit of conceptual stuff involving linked lists to get around. But the histogramming's basically been done for you. So, any questions about it? The homework assignment? When due? Isn't like next Monday? I think. Do you guys want to do on Wednesday? I think you should be able to do it by Wednesday. You want to do it on Wednesday? All right. Oh, it's not up on. It's not up on Canvas, is it? Okay. This Wednesday. Yeah. Right. Yeah. I agree with you, Mitchell. I think you guys could do it by this Wednesday. All right, fine. Enjoy your Thanksgiving. All right, it'll be due next Monday then. Bridges Shakespeare. All right, program assignments. See, if you got it done on Wednesday, then you wouldn't have to. You'd have Thanksgiving free and clear. You wouldn't have to. You wouldn't have anything to worry about. Getting the pitchforks. It's funny. You guys are funny. All right, there, and it'll be due on the 29th at 12. Cool. All right. Thanks for coming out, you guys. Sorry for hurting your brains with the unions, but you did ask for it, so I'm always willing to edgemify you if you have a question about it. So more fun to do it last minute. All right. Peace out, you guys. See you.